In this video, we're going to talk about linear approximation and an introduction to Taylor-Maclaurin. So in Calc AB, we frequently wrote the equation of a tangent line, and when we wrote the equation in a tangent line, we did so in the form of y minus y1 equals slope x minus x1. Now what we're going to do is we're going to go ahead and add that y sub 1 over to the other side, and we're going to write it as y sub 1 plus slope x minus x1. This puts it in a form that gets us ready for Taylor-Maclaurin's. So let's take a look at a linear approximation. So we're going to use a linear approximation about x is 1 to approximate the value at x is 1.01 for y equals x squared plus x. Now we choose x equals 1 because it's remarkably close to 1.01. Now if we stare at our curve over here as just an example, if we were to do a tangent line, it would be a good approximation for a short period of time. But as we get further and further away from that point, let's say over here, now our tangent line is not so good. So the idea is we can use a tangent line for a short period of time, but only a short period of time. So let's go ahead and review that. In order to do this, we're going to need a slope and a point. To get the slope, we're going to do the first derivative, so y prime is equal to 2x plus 1. We now want to do y prime of 1, so 2 times 1 plus 1 is 3. We now have a slope of 3. We're going to need a point, so we're going to plug our 1 into our function. If we plug in our 1, we get y is 1 squared plus 1, or y is 2. So we've got the point 1 comma 2. If we write this, we originally in Calc AB would go y minus 2 is equal to 3 x minus 1. But we're going to move that 2 to the other side now. So we're going to write it as y is 2 plus 3 times x minus 1. Now, that's the equation of our tangent line. We're going to use that to approximate 1.01. Now, obviously, if we wanted the exact value, it would be fairly easy to plug 1.01 in and get an exact answer. But we use approximations when the functions become more difficult. This is simply a basic example to get us started. So let's go ahead and plug in y equals 2 plus 3, 1.01 minus 1. So that would be y is equal to 2 plus 3 times 0.01. Ultimately, when we add that together, our approximation would be 2.03. Now, how close is that to the actual value? Well, if we plug this into our calculator, the actual value when plugged in is 2.0301. So comparing 2.0301, notice our linear approximation is fairly close to the exact value. Now, better than a linear approximation would be a quadratic approximation. Now, this is a preview of how to write a Taylor polynomial. So let's go ahead and start off the same way. We're going to start with our linear term. So our first derivative would be 2x plus 1. Plug in our 1, just like we did before. We get 2 times 1 plus 1 is 3. But now, because we want to go out to a quadratic, we're going to want to do a second derivative. So our second derivative would simply be 2. All right, so now we start off. We're going to need our point again. So y is 1 squared plus 1 is 2. So we've got a point 1 comma 2. So our initial statement starts off as y equals 2, the 2 coming from the value plugged in. Then we're going to have our slope, x minus 1. My pen died there for a moment. Now, when we go to do our quadratic term, in front of our x minus 1 squared is going to be our second derivative, which was 2. And we'll learn when we start doing Taylor polynomials that we're going to divide that by 2 factorial. If we were to do the approximation for 1.01 now, we would go 2 plus 3, 1.01 minus 1, plus 2, 1.01 minus 1 squared over 2 factorial. Well, this approximation comes out to 2.0301, which is actually the exact value. So a quadratic approximation would be better than a linear approximation.